This month we are very lucky to have Nick Eubank in the house to give us a rundown of Julia, which I think for probably many of us have heard of Julia, and we've been explaining many of the benefits of Julia, which Nick's going to talk about, but haven't actually used it or played around with it. So I know personally I'm looking forward to just kind of seeing some of the features available in Julia. And the 1.0 release is right around the corner, I think like in the next...
June, fingers crossed.
So just in a few months, it'll be non-beta, and it's been in beta for a really long time.
It's been about 5 years.
Right.
So at this point, I work a lot with version 0.6. We'll talk about this in a second. I mean, I think it's good and trustworthy to use, but they still want to tweak the syntax. And at the moment, most of the ongoing work is a compiler improvement. So.
Right. So at any rate, help me welcome Nick.
All right, thanks everyone for coming out during your lunch hour. So today, like I said, I'm going to be talking to you a little bit about Julia. We did the quick show of hands for who's doing what here. Our goals for today are kind of fourfold. First, I just want to give you a sense of why we might have a case for yet another language in a world that seems to have constant proliferation of these things. And then I'm going to try to give you a sense of some of the main features and things that Julia has to offer beyond just in terms of its infrastructure, but in terms of different features that you may be interested in as kind of an applied user. We'll do a little bit of hands-on tutorial, and I will try to leave you with as many resources as I can about where, if you really want to get into the language, kind of everything you're going to want is available. In the interest of time, it'll be a little bit light, but hopefully it should give you a good feel for the language and a sense of what's going on there. And then, as I said, so up on my GitHub page, there's a PDF, which I now realize should probably just be a little standalone website. It has an overview of kind of where you go for help, where you can find different packages, what the package ecosystem currently looks like, how you can install Julia, so on and so forth. So at the end of the talk, I'll make sure to leave you with the things that hopefully you want going forward. Let me also say, I know we have a lot of people from a lot of different backgrounds, so please feel free to jump in if you have any questions. I'm more than happy to handle those as we go. So a little bit about me, because I think it helps contextualize how I work with Julia and what it's meant for me. I'm a postdoc at the Center for the Study of Democratic Institutions. A lot of my work is working with tabular data, although most of what I've been doing with Julia has been network analysis. I do a lot of work with social networks and I'm particularly working with cell phone metadata. So I do a lot of diffusion simulations that have some weird custom tweaks. These are very large networks, and I end up running essentially millions of simulations. So the type of performance benefits that we get from Julia are kind of what moved me into this space. I have a fair amount of experience with Stata, R, and Python as well. A lot of my workflow is kind of NumPy, Pandas in the Python ecosystem. Coming from political science, I also have seen a fair amount of R, so I'll try to use those as kind of reference touchstones as we go forward. I should also say that I am a Julia user, and I am not a Julia core developer. So some of what I've learned has come from experience, reading the docs and talking to other people. When it comes to very low-level features of the language, I'm afraid I'm going to have to defer to somebody else, but hopefully that gives you a nice perspective of an applied user. In that spirit, I'm going to try to target this talk at people who are kind of used to working in Python or R. If you have questions that are a little bit more high-level, please feel free to shout them out, and I'll try to hit them. If you don't have a lot of programming experience and this feels a little bit too much, I just want to emphasize that that's more where I'm targeting it and less the language itself. I think one of the things I like most about Julia is I think it's a really nice language to teach, and it's relatively straightforward at a lot of different levels of engagement. So please don't be deterred if this talk turns out not to be targeted just at the right level for you. Okay. So by and large, our world of languages these days tends to be divided into two camps, right? We have the easy, nice to use languages, which is Python, R, MATLAB, etc., and then we have the languages that are highly performant, the whole C family, Java, and languages like that. By and large, in addition to just being different in terms of how quickly they run, we find that these languages tend to be interactive. So if you have tabular data, you can kind of tab out your variables and play with things. The easy languages are dynamically typed. You can change your variable x from a string to an integer, and you don't have to worry about that kind of thing. And most importantly, these easy languages tend to be fast to write, which is really nice for those of us who are kind of quickly prototyping code and working on a lot of projects. The downside, of course, is that the easy languages tend to be slow to run, right? If you write code purely in native Python, you're really going to tend to struggle with running time, particularly if you start working in kind of larger machine learning or larger data applications. By contrast, these fast languages, while they are awful to work with, tend to run at much, much higher speeds. And so the strategy that most people have ended up using for the last decade or so has been a hybrid approach, right? Where what we do is we work in R, Python, or MATLAB, and we call functions that are ostensibly in Python. But really, when you look at that function, all you're actually doing is calling a C library. Right? So most of the tools that we're actually using when we're working in R or Python are actually C libraries underneath the hood. Why does this matter? If what you want to do is exactly what the C library does for you already, you're great. It's wonderful, it's there for you. I think the problem is threefold. First, if you want to really understand what a package is doing, it's very hard to introspect if you aren't somebody who's a regular C programmer. Right? If you open up your Python library, what you're going to find is a call to a C library, and if you then try to track that down, you're going to find a very complicated library that if you are not a C programmer is almost impenetrable. And if you are a C programmer, it's just going to be harder to understand. Similarly, it's harder to modify a package. Right? As academics, we are by and large trying to move things in directions that they haven't been before. So if you need to calculate a different type of standard errors, or you want to run a slight modification on a library, if that library is actually hidden down there in C, and you are an R or a Python programmer, you're really in trouble if you want to try to make any modifications to it. And then finally, it's really hard if you want to write a package for other people. Right? The normal way that you end up doing this now is you prototype it in R or Python, you kind of get a sense of the flow and what you want, and then you go back and you rewrite the whole thing in C to make it available to other people in a way that works fast. I want to emphasize that all of this, I think, is true even if you know C and C# and all those different types of languages, but it's especially true if you don't. Coming from the social sciences, we basically had training up to the level of R, sometimes Python. And so asking people to learn an entire new language and one that's not particularly intuitive just to do these kind of iterative advancements on packages is really a giant leap. And particularly in the social sciences, but I think in other disciplines, you see a lot of people who get up to this point of being very good at R or Python, and then they just hit the wall because the next step of getting better involves a huge investment of time and energy that they generally avoid. So this brings us to Julia. So Julia is a relatively new language that's basically designed to solve this two-language problem. Julia is something that essentially feels just like Python. I'll show you a bunch of code snippets as we move forward, but the syntax is almost the same as Python. And yet, despite that fact, we end up getting a language that runs at very close to C speeds without any of the kind of terrible overhead that comes from writing a statically typed pre-compiled language. The other nice thing about Julia is fast that way, and as a result, the entire language is basically written in Julia, down to the definition of integers. Right? Because Julia is fast, they don't have to have a giant C implementation in the background the way you have with C Python that's kind of running the language separately from what you're interacting with. So if you learn to work in Julia, you also know how to develop Julia code all the way down to the base level. And if you want to look inside things, you can generally see it because it's all in Julia. Let me give you an example of what a little bit of Julia code looks like. I'm going to do most of my comparisons with Python. You'll see very quickly the people who wrote Julia were clearly Python programmers. You'll see some influences from R and MATLAB sneaking in places, but up at the top we have a Python function that basically says, let's take all the numbers from start to stop and add them all up. And then below we have a Julia function that does the same thing. You can see with the exception of Julia likes end markers, it's not white space sensitive, and Julia has a slightly different iterator notation. They basically look the same. The difference, however, is that when you execute these functions, you get about 3 orders of magnitude improvement running this in Julia. This exact code typed into an interactive console just on my laptop, 3-time improvement. This is not anomalous. These are a set of benchmarks comparing a number of different languages. Over here we have C, which is benchmarked at 0. This is our norm for a number of different computational tasks. There's all replication Jupyter Notebooks online if you want to see it. Julia, as you see, is sometimes faster than C, but generally, more importantly, within kind of an order of magnitude is C. It's down there around Go, Fortran. And crucially, it's doing much, much better than Python, MATLAB, and these types of libraries. So you don't necessarily need to understand this, but we're in academic settings. Let's just talk for a moment about why Python actually tends to be slow. So let's say we want to sum all the numbers from 1 to 1,000,000, so we're going to call this particular function. What's important to understand is your processor doesn't actually know what it means to add total in 1. It's not actually something that the processor can do in that abstract sense. The reason for this is twofold. First, not all numbers are created equal. In your processor, there's a little chunk of the processor that knows how to add together two floating point numbers, which are numbers with decimals. There's another chunk of your processor that knows how to add together integers. Neither twain shall meet. And so when you're running this particular function, one of the things that your program has to do is figure out, is total a floating point number? Is it an integer? Is it something other than either of those? And that's also important because in a language like Python, plus is what's called an overloaded operator. It actually does several things. If you try to add together two strings in Python, what you're actually doing is concatenating, which is an entirely different function. So the trick is that your computer, and in particular the Python compiler, has to check and find out what the type is of total. Is it an integer, a floating point number, or a string? Has to check the type of I, and then conditional on what those are, and has to figure out what it should be doing for the plus sign. And the real killer in this whole operation is the fact that in Python, when you go through this loop 1 million times, it's going to check the type of those variables 1 million times as well. What makes Python a nice interactive program is the fact that it evaluates each line when it gets to it, but it means it has to do this evaluation 1 million times, and that's incredibly costly. We're not just adding integers a million times, we're checking types, we're doing lookup tables on operations, and then we're deciding how to write the compilation for the machine code that will actually execute that on your processor. Here's where Julia differs. Julia treats every function as a standalone program. When you call a function in Julia, what it's going to do is say, well, let's look at this whole thing, not run it line by line. Let's say, if start and stop are both integers when we start this program, I know that total is an integer. I know that the start-stop iterator is just going to give me integers. That means total and I are going to be integers every time through this loop. I can figure this out by looking at the whole thing. And as a result, I don't need to check this 1 million times. It's never going to change because this function is a nice little self-contained vessel. And so I can write machine code that just does integer addition 1 million times. And that's a huge part of why Julia is so much faster at these types of executions. Any questions up to this point? Great. Okay. Not only that, it's going to keep a copy of that machine code. It's going to cache it. So if you call this function once, the first time you call it, it'll take a second because it's doing this inference. It's saying, okay, can I figure out what type total is, what type I is, let me then write machine code. Every time you call it subsequently, it already has the machine code. It doesn't have to think about it ever again. So it just runs the whole thing once. Python is not only evaluating at every line, but at every line it's writing new machine code and then immediately forgetting about it. This leads us to a couple notes that you want to keep in mind when you're thinking about performance in Julia. The first corollary is that Julia is only fast inside functions. Because when it sees a function, it knows that it has this nice self-contained little thing, it knows all the parts and it knows what's going on, it can compile those efficiently. If you just type this interactively into your console, it's going to run about at the speed of Python. This is the nice thing about Julia. If you do everything wrong, you get Python. By contrast, if you just wrap it in a function and then you run it like this, you'll get several orders of magnitude speed up. So the first rule in Julia is put everything in a function, even if it's literally just like taking your entire script and just putting a function definition at the top, the bottom, and calling it, it will get you massive speed ups. The second thing is that there's a way to write functions that ensures what's called type stability. So you can help this compiler by writing scripts where it's easy to infer that variables will always have the same type. So first, let me just say, when it compiles a function, it does so conditional on the types of the input arguments, right? So if you call this function with an integer, it's going to say, what can I do given that I got an integer as an input type? In this particular case, the problem with this function is that this will sometimes return an integer, and it will sometimes return a string. And that is not dependent on the type of the input argument. Right? So the compiler will not perform as quickly with this because it doesn't know when it gets called with an integer whether what it's going to spit out at the end is going to be an integer if the number is even, or if it's going to be a string if the number is odd. And if this function is inside another function, that kind of uncertainty will then propagate to everything else that's being run. There are easy ways to check this. It has utilities. It will tell you if you've given it something that it's not sure that it can quite infer types about. If you give it something that's type unstable, it's not the end of the world. Some of the current compiler optimizations that they're working on for the next release are meant to deal with situations where you know that it's either a string or an integer, but you're not sure which, but you also know it's not a floating point number. But this is kind of one of these rules, is when you want good, fast code, you wrap it in a function, you try to make sure that all the things in there stay the same conditional on the input argument. Okay. So let me talk just a little bit about kind of the nice features and bonuses that we get from Julia and the reasons that people, I think, find it very attractive. So one of the first ones is we can go back to just writing the loop. Right? If you've gotten used to working in Python or R, you're very familiar with this rule that if you want something to go fast, you have to vectorize it. Right? You are just not allowed to write loops because these loops take so long. In Julia, it is totally fine to write the loop. Now, you don't have to. There's basically this dot notation says, I just want you to vectorize the function that comes before it when you apply it to this vector x. But what's important is there's no penalty for writing things in loops. So if you have some kind of weird function, square root is a pretty straightforward one to vectorize. Most people will vectorize that. But if you're doing some weird manipulation and you want to write the loop, there's no penalty whatsoever. And in fact, in this particular case, it's marginally faster to write the loop than it is to vectorize. Native parallelism. Julia is meant to be a modern language, and of all the things we do these days, it is parallelized. So this is a simple piece of code. The first thing just says, I want you to start up 3 workers. This is on your laptop. It'll just allocate them as separate processes and claim different cores on your computer. This is very easy to set up on Slurm, where essentially you load a library that's called Cluster Manager, and then when you, run add procs, it's just going to create them within your Slurm allocation. And then this loop just says, I want you to parallelize the steps in this loop, and for I through 1 to 1,000,000, I just want you to have workers execute this code, which is create a random Boolean, little coin flip example. What this loop will do is take care of all the issues of sending information about what you want to do, send any data that you need to all these different workers. It'll load balance, so one of them ends up slowing down. It'll make sure the jobs don't get kind of allocated to it while it's still busy and the other ones are resting. It'll bring them back. It has a reduce function. It'll add up all those inputs, and then it'll give it back to you here. Full parallelization in 1, 2, 3, 4 lines. Oh, also, this is a very small point. These underscores are totally allowed in Julia, and though I know it's a small thing, it's one of my favorite features. We've all sat there pointing at our screen, like trying to count the number of zeros we type, right? Also, if you're an international, this is not checked to be at 3 intervals. So if you're Indian and you want to do lax, you're allowed to kind of shift that over to 1,00,000,000. But it's really nice for readability. You can also do this for shared memory parallelism, which if you kind of ever try to do this is just an absolute nightmare. So there's a native type called a shared array. You can do something where you're all modifying the same array. Julia is taking care of the fact that we're all trying to modify the same thing in memory at the same time, and it will deal with all this messaging back and forth to the various workers. Again, 4 lines. If you have big jobs, so say you want to apply a function to a bunch of different items, basically using like a map function, there's a pmap function. In this example, this will execute the single value decomposition function across each of the items in a list of matrices, and it will bring them back. If you've allocated workers, it does it all. Sends out the data, sends the function definitions, gets it to execute, brings it back, and gives it all to you in a list. Okay. It's really good at linear algebra. So there are lots of things you can do in linear algebra that are where the way you want to do it depends a little bit on the nature of the matrix that you're working with. So factorizations are kind of the most common example if you want to solve a system of linear equations. If your matrix is symmetric, there's a way to do it that's like 10 times faster than if you have an arbitrary matrix. The compiler in Julia is very good at recognizing, first of all, if your matrix has an unusual form, lower diagonal, tri-diagonal, diagonal, symmetric, any of those types of things. Not only that, but if you've worked with these types of matrices, you know occasionally just because of floating point errors, right? Numbers with decimals in computers are like kind of all approximations, and so you can end up in a situation where like, you know your matrix is symmetric, but the computer doesn't think it is because the 43rd decimal is slightly different above and below the diagonal, in which case you can just declare to it, FYI, this is tri-diagonal, treat it as such, and it'll say, all right, great. And it will dispatch when you execute functions like factorization to the right algorithm to make sure that it's doing this as efficiently as possible. This, I will say, is the one place that I know of where Julia is not written in Julia. At the very base level for doing factorizations, it's calling the LAPAC, which is a Fortran library from the 90s. This is just one of those things where people have spent so much time optimizing, and it's so important, they figure the factorization code can do whatever it needs to do. So at the very bottom level, there is, in fact, some Fortran code there. Julia was explicitly made for people who are doing numerical computing, academic research, sciences. As a result, it has a lot of inbuilt types that are the types of things that scientists use but web programmers never would. For example, rational numbers. In Julia, you can have 1/2, which is not 0.5, it is 1/2. And it knows how to deal with fraction, basically fraction manipulations that are in exact terms. It knows how to do imaginary numbers right out of the box. It's entirely happy with I. It has a big int library, so if you know you're going to work with just obscenely large integers, it has all that kind of baked in. Plus, because all these types are written in Julia, that means that if you write your own type that does something unusual, it's no different than the inbuilt ones. It will run just as fast. If you have a specific application and you want to come up with a slightly unusual data type, it'll run as fast as the inbuilt integer library within Julia. Okay. If you have a C library and you really need it, there are accommodations for you. So this is a line of code that essentially just calls the clock function from the library libc. We have to tell Julia what it's going to get back. It's an int32. And then you can pass any arguments to it you want. In this case, we don't need one. That's a C call. One line of code, no extra libraries, nothing like that. Similarly with Python, if you have a Python library you really need, you can definitely bring it in. You just say, using pycall at pyimport math. Basically what this is doing is it's calling the math sign function from Python, calling the math pi constant from Python, and comparing it to the Julia ones. This comes out to 0, very reassuring. But this is kind of all there is to pulling in Python. As I said, a lot of the people who work in Julia, I think, are coming from the Python background, and so this is something that's been relatively well accommodated. Though with that said, I've yet to actually find an occasion when I needed to use any of these. This is a dumb little thing, but it's kind of fun. Julia is fully Unicode happy. That means your variables can be any valid Unicode character. You can assign the value of 5 to a smiley face. If you are teaching, you can actually use the same Greek characters as variable names that you are writing in your code. If you have a LaTeX paper and an associated code for replication, you have some big formula for your optimization function with lots of Greek characters, it just goes right into Julia, no problem. The stats people love this. If you go into the distributions package, which gives you like random variables for all the various distributions, it's just like all written in Greek. They just totally love this particular feature. Right, metaprogramming. This is not something that I think most of us deal with, but if you're coming from like Lisp, you'll find it fun, and if you really get into Julia, this is something that's nice to be there. Because Julia is written in Julia, it has a parser and a compiler for Julia code written in Julia. As a result, the language has to be fully capable of writing Julia code and manipulating Julia code. So Julia, like a language like Lisp, is entirely comfortable writing Julia code that manipulates Julia code objects. This is very nice in a number of kind of unusual settings, but something to be aware of if you're into it. Okay. We'll get into some specific examples playing with the code a little bit. Let me just give you a quick overview of things you want to kind of keep an eye out depending on where you're coming from. If you're from the land of Python, functions are entirely comfortable with duck typing. We'll talk about that a little bit more. Duck typing is where if you have a function where the input arguments seem like they should work with the code as written, they will work just fine. If you don't know what it is and you usually work in high-level languages, this seems like obviously what things should do, but this is not what all languages do. It's passed by reference. It has iterator objects, right? So you can do for I in a vector, and it knows you want to go through all the different items within it. It has list and array comprehensions, all that like nice syntactic sugar that just kind of makes it a little bit easier to write things. Things that are a little unfamiliar. So I think the biggest one that people want to be aware of is there's no integer overflow checking. Right, so integers are just a series of zeros and ones, and if you take a string of all ones and you add 1 to it, it becomes 0 and kind of rolls over to the backside. Checking for those costs about 10x in terms of full performance. Just in native Julia, there's a library here called safeints. It's a little bit more optimized. It does integer checking, but slows code down by about 3x. So you just want to be really careful. On most people's computers, the native type of an integer is int64, which means you only overflow if your number gets bigger than 2 to the 63, which is not super common, but you know it can happen, so it's just something to be aware of. It has a built-in package manager, so you don't have to deal with Anaconda anymore. You don't have to worry about distributions. It's all entirely integrated. This is one of the things that's going to change a little bit in the new release. There's no current namespaces, which means you can get like function name collisions. If you load two libraries and they both have a function called sum all the elements, the second one you loaded will be the one that is available to you. They're going to change that in the next version, and we'll get back to this world where you kind of prefix with a dot, but it's not quite there yet. It's not white space sensitive. Indexes start at 1 and not 0. The first item in a list or an array is a 1. This apparently caused a near civil war, but it is now firmly baked into the language. And then there's a concept called multiple dispatch for functions, which we'll talk about a little bit more in a minute. If you're an R user, things you will be familiar with. It has multiple dispatch. Different methods are going to be called depending on the types of the input arguments. It has a built-in package manager, so if you've ever tried to move over to Python and hated that you can't just like load a library right in your code, now you can. Things are unfamiliar, there's no integer overflow checking. The big thing to be aware of is that Julia uses what's called pass by reference. Most languages other than R have this behavior, which is referred to as pass by reference. There is a handout on my GitHub page. It's a little PDF that walks through it. If your life has mostly been R, you need to read about this. It's a great way to get yourself caught. But because most programming languages do something like this, I don't think I've ever seen it really explicitly talked about in a Julia tutorial. So if you are an R user, this is a really important thing for you to kind of take a look at and make sure you understand. If you're Python, it's what you're used to anyway. And then lastly, as I said before, it loops for fast and vectorized functions. So you don't always have to put these in these weird vectorized events. Okay. As I mentioned, we're not quite at 1.0 yet. The current release is 0.6.2. I think it's very safe and stable. I use it for my research. It doesn't make me uncomfortable to be running it to any degree. But it is the case, if you're not used to kind of software version norms, the norm is basically before you get to 1.0, as you move from version to version, you're allowed to change the syntax in the way that makes old code not work. So if you write code for 0.6, when 1.0 comes out, it will be the case that you will find that some of your code breaks and you just have to go through and clean it. To make that easier, the first release of 1.0 is actually going to be called 0.7. 0.7 is 1.0 plus error messages that pop up if you're still running 0.6 code and you run into a conflict to keep it informative. If you code against 0.7, you're fine. They just want one release that has lots of warnings so people who have old code can adjust their code, and then they'll take out the warnings and call it 1.0. But this is going to be the same thing. I think the only thing that they're still fighting with a little bit, well, here. So there's going to be a couple changes. There's a number of syntax changes. They're not huge. You can find them all online. The main change is they're doing a big change to the compiler and the way it handles missing data. This is something that everyone is super on board with and taking their time to make sure they get right. It's basically one compiler guru working in a back room, so nobody's quite sure how long it'll take, but the hope is that this will be done by the Julia conference this summer. I think everything else is now done in the 0.7 release. You can download it and run it if you would prefer to do that. And then, as I said, we're going to update the package manager. If you use the current one essentially clones the entire Git repo for every package that you load. It's very convenient for development, but it's kind of slow and a little obnoxious. And so the new one will not kind of pull down that much data, and it'll be a lot lighter and a lot faster. That's kind of the main difference. So it's something to be aware of moving forward. If you're playing with it now and you load a package, the reason it's slow is it's cloning the entire Git repo for whatever library you tried to install. Okay. So a little bit of hands-on and playing with stuff. Julia is taking the model that a few other open source projects have done, including Linux, which is there is a for-profit group called Julia Computing. They include some of the core developers for Julia. Julia itself is free and open source, but if you ever want to set up your company, they are more than happy to offer paid consulting advising. But one of the things they have set up, which is very nice, is an online place where, without doing any installing or anything, you can quickly get up and running with Julia. And they include a lot of very nice tutorials. So we're going to go through two of these that I think are kind of most important and salient in the interest of time. But they're all there, and as I said, this is a great way to learn if you want to going forward. So if you want to play along, juliabox.com, and then you just log in with one of your accounts. Oh, I moved offices. Oh, it's because Will logged into the account. Got it. These are all in the form of Jupyter notebooks. Raise your hand if you've worked with a Jupyter notebook before. It used to be IPython notebooks. Okay, great. Seems like most people are super comfortable. Now we find out whether you can stream a video while also loading web pages. Well, we'll find out in a minute. So while this is loading, if you want to learn more about Julia, as I said, there's kind of a resource page on my GitHub, which is a PDF because as an academic, I'm always working in tech. There are links to the main forum, which is kind of a great place to go for help. It's on Stack Overflow, and there's plenty of people there too, but the kind of the forum is a nice place for simple questions. There's one page that has low frequency announcements, which is where you can make sure you hear when 0.7 comes out finally. There's also information on different interactive editing options. So Julia comes with a console. It's relatively well featured. It feels a lot like IPython, basically, just kind of natively. But it's also the case that you can get kind of a nice interactive development environment. The one most people are using is called Juno. It's built into the Atom editor, ATOM, which comes from GitHub. So there's installation suggestions up there. We'll see if we get to do this. Not looking good. Huh? I'll give it a minute because the tutorials are really nice, but this is free and available. So up here there's, I think, 14 different individual tutorials that work through everything from first what a Jupyter notebook is to simple variable assignments, simple mathematical operators, loops, functions, string behavior, linear algebra optimizations, various benchmarking things. It takes about, say, an hour and a half to 2 hours to work through kind of fully, though if you're a Python person, you'll probably go a little bit faster. And it's also the case that you can find, Julia Computing has released YouTube videos where people just walk through them with you. There's a link on the PDF. So if you're interested and you want to do it with somebody, just go watch the YouTube video and work through these. By the end, you'll be in great shape. Okay, excellent. So the main one is just Intro to Julia. There's also a Spanish language one if you want to go that way. And we're going to look, in the interest of time, just at the functions one, and then we're going to talk a little bit about multiple dispatch. All right. Great. So function definitions are kind of as you would expect. It's very straightforward. Looks, as I said, an awful lot like Python. The one thing to note is string interpolation. So in Python, this used to be the %sign and is now the .format command. In R, you do the paste of all the things together. In Julia, you just put a $sign, and it will then take whatever name is, and it will stick it into that string and return the string. So define a function there. Define a function that's just squaring the input argument. You'll see by default the last argument gets returned. You can also use an explicit return statement if you want. Say hi, square a number, very straightforward. You can also do one-line definitions, right? So if it's something super simple, you just define the new function like that. One line, very straightforward. Julia does support anonymous functions, which is where you define a function, but you don't actually give it a name, so you can't call it. You might wonder why you would ever want anonymous functions. They end up being sometimes useful if, for example, you're using a function that wants a function as an input argument. You don't want to name it and carry it around, so you just type it in directly. But the syntax here basically is, this would be an anonymous function where it takes name as an input and then it just prints this thing. So you can pass that to a function if you want. You can make an anonymous function, assign it to something if you'd like. All pretty straightforward. Duck typing. So up above, we define this function, say hi, and we show that you can use it where you pass a string for a name, right? But as I mentioned, it's also the case that that string interpolation works for any other type of variable. So I can pass, say hi, a number, and it will just interpolate the number into the string, and it'll print it, and it has no objection. Similarly, our f function, which just does f of x is equal to x squared. X squared is just syntactically equivalent to x times x. So if we pass f an array, since multiplication is nicely defined for a 3 by 3, it's just going to execute that way, right? So this is familiar to how most kind of higher level friendly languages work fine. The asterisk symbol is also the concatenation operator in Julia, so it's not the plus sign, it's that. And so for the same reason, f of high just gives you high, high, right? Okay. So this is where we start getting a little bit to the idea of pass by reference. So some functions will modify an item and then give you something new back, right? So we have this vector, 3, 5, and 2. We sort it, we get this new thing, but we never assigned the thing that we sorted to anything, and so the original item is still 3, 5, 2. However, if we use sort exclamation point, then we will see that we have mutated the original item. We have changed it. This exclamation point notation is a norm within Julia. Any function that changes the input argument in place should at least, have this exclamation point at the end. If you don't change the input arguments, you do not put a $sign on it. It's just a nice thing where a lot of languages you have to like test to figure out if you're mutating things. Julia should always be right there in the naming convention. We also have map functions, which basically say, take this function f and apply it to each of the items in this list. Right, so this is going to return the square of the first thing, the square of the second thing, and the square of the third thing. For reasons that are a little bit weird, there's another function called broadcast that's essentially the same thing. Map and broadcast differ only in the way they handle errors when they come up. Otherwise, they're the same. But as I said before, there's also this dot notation. Dot is exactly the same as this broadcast function. So f dot, the vector 1, 2, 3, just says apply the function f to the first item, the second item, and the third item. And so we get the same thing. There are array comprehensions. If you're from Python, this will feel kind of familiar, although this is not creating a list, it's creating an array. So what it's doing is it's running the loop in here, and then each step of the loop, the thing that it creates, which is going to be I plus 3j, it's going to put that into an array as the next item. This is the equivalent to essentially creating an empty array, creating a loop. As you go through the loop, assigning elements into each spot in order. Yeah?
It's probably a good point to note that you don't need the asterisk between the 3 and the j.
Yes. Thank you. Yeah, so we can skip those. The range things you're going to be familiar with from R, know that they include the last element, right? Because we're counting from 1, we include the last element. So unlike range in Python, which starts at 0 and drops the last item, this range iterator will give you the last item. Also, it is an iterator. It does not immediately correct. Like if you do 1:1 million, it's not going to create an array with 1 million items. It takes a lot of memory. It's just an iterator that knows how to work through things. Okay, great. So now multiple dispatch. I think just in time. Here's the thing that's going to be most weird to you if you are coming from Python. As we discussed before, if you write a generic function, Julia is entirely comfortable taking arguments of different types and just executing the code against it. Ah, right. Well, we can't do it for that one because 2 vectors can't be multiplied directly. The dimensions don't work. It is also the case that you can write a function, what's actually called a method for a function, that is specific to a type of input arguments. So foo in the language of Julia is called a function, but we can write different methods, all of which are called foo, but are actually different functions that will get called depend on the type of the input arguments. Right, so in this case, I will say foo is defined for x and y, where x and y are both strings. This double colon says I am asserting the thing before it is of this type. If I run it with 2 strings, it runs great. If I try to run it with 2 integers, it says I don't have a method matching that. Right? You defined a function that takes 2 strings, and you just gave me 2 integers. What am I supposed to do with that? So now we can create a different method. It's also called foo. We have the same function name, but this one is defined for integers. And so now if we call it, we get my x and y are both integers. Notice these two methods, though they have the same function name, are calling different code and doing different things. This is the second reason that Julia runs very fast. Lots of functions that are available in Julia are actually lots of different functions that have been optimized to deal with different types of input arguments. Right, so unlike Python, where you get one thing and then in it you write if the type is this, do this, if the type is that, do that, et cetera, in Julia we're actually calling different methods behind the hood. Right, so the original one is still there. If I give it two strings, it still says, hi, these are strings, and doesn't talk about integers. There's the, right. The methods function will show you what all has been defined. So this is saying, under this function foo, I have two methods. One takes two integers and one takes two strings. And you can do this to anything. As I said, because Julia is written in Julia, we can even look at all the methods that are defined for the plus operator. There are a lot of methods written for the plus operator. This is one of the reasons Julia can be fast, is when you call plus for two things, it's calling the code that's going to be able to do it most effectively for whatever you're adding together. These are all also, just to be clear, written in Julia, and if you click the link on the right-hand side, it will take you directly to the code in the Julia language. You can ask it which method it's going to call before you call it. So at which says, which method are you going to call if I give you foo of 3 and 4? Similarly, you can do it for any base function, because, again, base functions are the same as user functions. If I say which plus are you going to call, it says I'm going to call the plus operator for two floating point numbers. Julia also has abstract types. These are types that are not quite something the processor can deal with, but are categories that we think of kind of normally. Number is one we use a lot. Integers, floating point numbers, int 32, int 64, int 8, these are all numbers. They all fall into this category. So if you want to define something for numbers, any of those things, you can just use the higher level category. So now if I give it to floating point numbers, because floats are elements of the number type, it will run just fine on the floats. The last thing you can do is write a fully generic function back to the duck typing. This is what's called often called a fallback function. Right? This one has no requirements whatsoever. And so if, for example, I make a vector that has 3 random items in it, and then I pass the vectors in, we haven't defined a method for vectors, and so it's going to go to the fallback method and go to the generic function that we wrote. Julia will always try to go to the most specific signature it can find. Right? So if we give it integers and we define for integers, it'll go to integers. If we give it floating point numbers and we didn't define floating pointers, but we did define numbers, it'll then go up to numbers, et cetera, et cetera. Does this feel comfortable for people? It's definitely the weirdest part of the language. It's one of the things you don't have to worry about if you don't need to, but it's very helpful for understanding what's going on. And I think those are the two most important. Right. So there's this whole set of tutorials. If you work through them, they're really well commented, well designed. As I said, there's a YouTube video where somebody walks through them with you, which is very nice. They include wonderful things like the fact, if it will load, as I said, you can assign a string to the variable smiley cat. You can do manipulations like if smiley cat is 1, smiley face is 0, and sad face is -1, you can get smiley face plus sad face equals happy face. It's true. It's a very nice language. All right, last things to leave you with here are, great. So like I said, there's this link up here, should give you a fair amount of stuff. How to install it, it's very easy, particularly, yeah, it's relatively easy. It also includes a guide for how to use Julia on the ACCRE system. So ACCRE does not currently have Julia in the module self-loader, so you have to download the binary for Julia. Runs fine, just drop it in your home folder and add a symlink. And then it'll run fine. When they get to the 1.0 release, they're going to put it in the modules and it'll run the same way as everything else. There's examples for how to do parallelism with Julia on the ACCRE system, which, as I said, is very straightforward and very nice. And then there's an overview of the package ecosystem. One of the worst things, of course, is always to I want to do X, what's the right package? What if I invest in a package that turns out to be written by some random person who's not taking care of it? So there's a guide to all the big ones. The ones most of you are probably likely to use is dataframes.jl. It lets you basically have tabular data where each column is a single type, but different columns can be different types. It's the same thing as data frames in R. Everyone uses it. It's very nice. And I think, let me just see if there's anything else in there. Numerical optimization algorithms are in there. Trying to think what packages are particularly useful here. Julia Plots is really nice. So they have a common front-end interface for all plotting. It can then be attached to lots of different backends. So if you like plotting, the JavaScript library for interactive plots, if you really want to type plot libraries, all those different things. There's a single common interface provided by plot.jl, and then you can just change whatever backend you want to have associated with it. I/O libraries, numerical optimization. Like I said, most of the people doing this are doing numerical optimization, so I think these are pretty good. We have all the weird non-derivative based Nelder-Mead type optimizers and things like that. Lots of random number generators. And a great network analysis library, which I know is what I've been using most. All right, I think that's it. Any questions? All right, thank you for coming.